So now that we've made these molar mass conversion factors, we can start to use them to solve problems, right? So when we take these conversion factors and we use them to solve problems in the real world, we're going to either start with a mole quantity and use this conversion factor to cancel out the units, or we'll start with a gram quantity and use this conversion factor to cancel out the units. All right? So now that we've gone over how to make conversion factors with a single element, now I'll show you how to make conversion factors with multiple elements. All right? It's very simple. I hope you guys understand that we took the atomic mass units. We got that number directly from the periodic table. It's the average atomic mass. That's the number we got here. And then we used Avogadro's number, which is 6.023 times 10 to the 23rd atoms in 1 mole of sodium atoms. And then we used that relationship right there to create an equality with this atomic mass units. Like I said, we don't need to know why atomic mass units equals grams over mole. That'll just cloud the fact. That'll just cloud the concept right now. But atomic mass units become equivalent to grams per mole, right? So we use 1 mole of sodium atoms equals 22.99 grams of sodium, and we use that equality right there to set up our molar masses. All right, so 22.99 grams of sodium is 1 mole of sodium. 1 mole of sodium is 22.99 grams of sodium. All right, so it's a really easy process to make these molar mass conversion factors. All right, so I hope you guys all got this. If you haven't, it's a video. You can go ahead and rewind. All right. So again, like I said, now I'm going to show you how to obtain the molar mass of something like, we'll do CH4. So we've gone over what those elements are and how to find the atomic masses. We've already been over that in chapter 1 and most of chapter 3. So we're going to find out the molar mass of CH4, right? So that's the molar mass of carbon covalently bonded to 4 hydrogens. Later on in the semester, we'll talk about covalent bonding and what that entails, molecular structure, everything like that. Right now, you don't need to know that. You need to know nothing about CH4, which is methane. You need to know nothing about it other than it contains 1 carbon atom and 4 atoms of hydrogen. That is all you need to know to figure out the molar mass, right? So the molar mass is an additive quantity, which means that we can add the separate units of molar mass to make a total molecular molar mass, right? So here's what I'm talking about. Let's take methane, for example, all right? So the molar mass of carbon, walking over here, I'm going to look at the periodic table. At the bottom of the element square is a red number, right? It's 12.001. Carbon is equal to 12.001 grams per mole, right? How did we get grams per mole? Well, that's because we said 12.01 atomic mass units, and an atomic mass unit is equivalent to grams per mole. So what does this describe? This describes there is 12.01 grams of carbon in 1 mole of carbon. So what does that mean? That means 6.023 times 10 to the 23 atoms of carbon is equivalent to 12.01 grams. You might ask yourself, why, if we used carbon 12 to set the standard for AMUs, is a 12.01? Well, again, it's because that atomic mass up on your periodic table is equal to the average atomic mass. And there's also carbon 13. So what we see here, and carbon 14, what we see here is we get an element, we get one of our elements into its molar mass form, right? So carbon is equal to 12.01 grams per mole, all right? I'm being very repetitive because it's very simple, all right? So many chemistry students make this so much harder than it is, trying to figure out all kinds of stuff, trying to tackle and wrestle with things. You don't need to know a lot to know that that red number at the bottom means grams per mole. Once we get the units, we can move the units around. So let's get the total molecular mass. So hydrogen has 1.008 grams per mole, right? I get that from the periodic table, and that's the atomic mass, right? So we have the molar masses of each of our two component elements, right? But if you know, if you notice this number, that number is what we call a subscript. You might ask yourself, well, what is a subscript? Well, a subscript, you guys have all used it, right? X1, X2, X3 describes the quantity of the thing that it's attached to, right? So that the subscript means that there are 4 hydrogens in that molecule. Plain and simple, that number means there's 4 atoms, right? So then when we use this, we say, okay, there's 1 carbon atom, which is equivalent to 12.01 grams per mole. So now we have the mass that our carbon adds to our methane molecule. Well, then we say, but there's 4 hydrogens. So what's the mass that hydrogen adds to the methane? Well, hydrogen adds 4 times H, right? 4 times the atomic mass, which is equal to 4 times 1.008, which is equal to 1.032 grams per mole. Right? Sorry, not 1. 4.032 grams per mole. Right? So now we have our numbers. We have our 2 molar masses. Well, now it's really simple. We just add, because we said molar mass is an additive quantity, so we can add it. So now we just add these two. So this is 240.61. So the molar mass of methane is 16.042 grams per mole. Well, what does this mean? Why do we do this? Why is this important? Why is this important to you? Well, when I try to describe the macroscopic scale of methane, let's say we're trying to describe the amount of methane in this room, but we're trying to pick out individual molecules. Well, I can't say, well, 1 atom of methane was weighed on a scale to this accuracy. We can't do that. But we can say 1 mole of methane weighs this. So now let's take it into atoms, right? We can do that using the mole quantity. Well, how do we start about doing that? So we've added our molar masses, right? We've added them together. Well, now we can make our conversion factors, right? So this means grams per mole. So then this is 16.042 grams per 1 mole. Right? We can also make the opposite, which is 1 mole is over 16.042 grams. Right? And this is of CH4. So you can see that for each individual molecule, there would be a different molar mass. Right? So now we have everything we need to proceed with the experiment. Right? We're going to take a number and we're going to go walk through experiment 2. So now we've talked about Avogadro's number. We've talked about the mole concept, how the mole is intrinsically related to Avogadro's number. It is a unit describing the number. So we've talked about the mole concept. We've talked about molar mass, how we get each individual molar mass, elemental molar mass, and now we've just talked about molecular molar mass. Well, now we're going to talk about experiment 2. What's its purpose? Why are we doing it? Well, experiment 2 demonstrates to you, the student, why moles are so important and how it demonstrates things in our macroscopic world, right? Because again, I've said this 1,000 times, I understand why chemistry is so hard. You can't hold it, you can't touch it, you can't see an individual atom, you can't do it. So why is it so hard? You have to think about it, and you have to use arbitrary numbers and what seems like arbitrary quantities to describe that world. Well, those arbitrary units and those arbitrary numbers aren't necessarily arbitrary, but they're really easy to use, right? So let's talk about experiment 2. So when you walk in, your first number 1 says measure out 1.25 moles of sodium chloride. Right? It says that. So what you'll do is you'll sit down with your group and you'll look at this and you say, how do we measure this? Well, you'll have a beam at your lab station. So how do you measure out 1.25 moles of sodium chloride? Well, it's really simple. You take moles and you use that to convert into a mass. Well, the first thing we have to do is we have to go through a molar mass. So the first thing we have to do is we have to figure out the molar mass of sodium chloride. Well, we've already gone through, we've already said sodium is equal to 22.99 grams per mole. Right? We've already said that. We already know the molar mass of sodium. It's really easy to remember. Chlorine, not so much. Right? The average atomic mass of chlorine is equal to 35.45 grams per mole. Now, mind you, again, molar mass is an additive quantity. So we can just add multiple molar masses together if they're in the same chemical formula. Luckily for us, this is a one-to-one correspondence. So we get 1 times that number and 1 times that number. We add them together. 4, carry the 1. That's 13, 14, point. Carry the 1, 18. 58.44 grams per mole. So now we know that the molar mass of our sodium chloride is equal to 58.44 grams per mole. Right? Well, what are the 2 conversion factors we can make from that? I'll go over here and we're going to say 58.44 grams per 1 mole of sodium chloride. Right? We can also make the conversion factor 1 mole of sodium chloride is equal to, hopefully you can see this, 58.44 grams of sodium chloride. So now what do? Now we have our conversion factors, we have our molar mass, but it's saying measure out 1.25 moles. So you're asking, where does this molar mass get us? Why are we doing this? This is a very long form way, right? Well, we have 1.25 moles of NaCl, 1.25 moles. Well, now, which one of those conversion factors gets us to cancel out the unit moles of sodium chloride, right? Which one? Well, we have grams over moles and moles over grams. Well, we need a number, a conversion factor, that when multiplied by that, cancels out moles of sodium chloride. So what do we need on bottom? We need moles of sodium chloride. So now we've canceled out that unit, right? We've gotten rid of the moles. Now we need grams. We want mass. So we want grams of sodium chloride. Well, what conversion factor gives us that relationship? Well, obviously, these units match up with these units. So let's use that conversion factor. So we're going to put 58.44 grams per 1 mole. Now, I'm not going to give you the answer because this is half the lab, all right? But this is how we set it up. Do you see how we end up with the mass of sodium chloride? Now, you'll have to do this with atoms, but remember that 1 mole is equal to 6.022 times 6.023 times 10 to the negative times 10 to the 23rd atoms, right? So let's do a problem that relates that. Let's try to figure out, let's do number 2. Let's do number 2, all right? So we're going to say follow the same basic principles that we've been following all along. All right? So, well, let's move back to the pre-lab assignment. All right? Let's move back to the pre-lab assignment. Let's go for how many molecules are in 6.25 grams of water? right? So the first thing we need to do, molecules comes from moles, right? So we need to find a molar mass. So the molar mass of water, oxygen, 16.00 grams per mole. And then we have 2 times H, which is 2 times 1.008, which is equal to 2.016 grams per mole. Well, now remember, molar masses are additive, so we add these two quantities up and we get 18.016 grams per mole, right? That's the molar mass of water. So now we have a relationship between grams and moles. And what's the mole concept? Well, intrinsically in the mole concept is Avogadro's number of molecules, Avogadro's number of atoms, right? If we find the molar mass, we find the mass of Avogadro's number of molecules. So right here, we have the mass in grams per mole. So now let's start with our unit, 6.25 grams of H2O. Now, since we've done so many of these, I'm going to skip the conversion factor step, right? We just don't need that at this point. So let's go through and let's figure out what unit we need to cancel. Well, we need to cancel grams of H2O. We need to cancel that. We're trying to get to moles. So we need moles of H2O on top, right? Well, now, what number is this associated with? This number is associated with grams. So this number goes down here, 18.016, and this is 1 mole, right? So now we need a conversion factor that relates moles and molecules. Well, what is that, you ask? Well, it's up there on the board. It's Avogadro's number. So we need to get rid of the unit moles. So we put moles of H2O down here, and we put molecules of H2O up here. How many molecules are in a mole, you ask? Avogadro's number. It's always Avogadro's number. 6.023 times 10 to the 23rd molecules in 1 mole. So you're going to take in your calculator and go 6.25 divided by 18.016 times 6.023 times 10 to the 23rd. That gives you how many molecules are in 6.25 grams of H2O. So now, with all this information, right, you'll come into class and you'll perform experiment 2 gracefully and beautifully without harming anything or without running out of time. Have a wonderful night, you guys.